Hello and welcome. In this video, I'd like to say a little bit about this number, e to the power pi, sometimes known as Gelfond's constant. So it evaluates to about 23.14, and it's quite a nice expression. It combines one of the most fundamental objects in calculus, namely raising e to the power of a number, with, well, I don't want to say that pi is the most fundamental number in circle geometry. It's half the most fundamental number in circle geometry, which is 2 pi. Okay, so some interesting facts about this number. Firstly, if you raise it to the power of the imaginary unit I, you get -1. So this number is a solution of the equation x to the I equals -1. So this I, if you're not familiar with complex numbers, this is not a positive number or a negative number, so it doesn't lie on the usual number line. Rather, it lies off the usual number line within a number plane that also includes the usual number line, and it's characterized by the property that I squared is equal to -1. And one of the marvels of mathematics is that it turns out that, roughly speaking, there are lots of limitations of the number line that are perfectly solved when extending to this number plane. I won't go into any of the details here, but you hear about invention versus discovery in mathematics. Well, this number plane with a square root of -1 perpendicular to the usual number line, it's not an invention, it's a discovery, and I'd say it's one of the most important discoveries in the history of mathematics. Okay, so as I say, Gelfond's constant is a solution to the equation x to the I equals -1. Now, it's not the only positive solution to this equation. There are other positive solutions, namely the odd powers of Gelfond's constant. And so, in some sense, Gelfond's constant is the simplest positive solution to this equation. Okay, and now another interesting fact about Gelfond's constant. If you raise it to the power of the square root of 163, you get something that's ridiculously close to an integer. Slightly less impressive. If you subtract pi from Gelfond's constant, you also get something that's fairly close to an integer, because, as you can see from looking at the decimal places, it's approximately equal to 20 plus pi. Okay, well, now let me tell you a fact about this number that you probably won't find on the Wikipedia article. Imagine we have a disk that's fixed to a vertical wall, so it can't move and it can't rotate. And imagine we wrap a string around this disk, and to one end of the string we attach a 1 kilogram mass, and we also attach a mass to the other end of the string. Now, you may have seen setups of this form in high school mechanics, where it's specified that there is no friction between the string and the disk. And so, in this case, if the mass on the left is greater than 1 kilogram, then the system will slide this way. But if the mass on the left is less than 1 kilogram, then the system will slide this way. Okay, but now I'm going to be interested in the case where there is friction between the string and the disk. And so, now in this case, if the mass on the left is a tiny bit more than 1 kilogram, what will happen? Well, the system will just remain in equilibrium because of the friction between the string and the disk that prevents sliding. And so this naturally leads to the question of what is the largest mass that I could have here on the left while maintaining that the system is in equilibrium? Well, the answer to that question is going to depend on how rough the contact is between the disk and the string. And so I'm going to specify this roughness by saying that the coefficient of friction between the string and the disk is 1. Now, what does this mean? Well, imagine I have a flat horizontal surface that's made of the same material as the disk, and imagine I have an object resting on this surface that's made of the same material as the string. Now, if I apply a very small horizontal force to the object, what will happen? Well, the object will remain in equilibrium, again due to the friction between the object and the surface that prevents sliding. And so, again, this naturally leads to the question, what is the largest horizontal force that I can apply to the object while maintaining that the object is in equilibrium? Well, what is meant by a coefficient of friction of 1 is that when the contact between the two materials occurs in this configuration, the largest horizontal force that can be applied to the object while maintaining equilibrium is precisely the weight of the object. In other words, if I imagine that there are handlebars attached to the object, such that I can either hold on to the handlebars and push the object horizontally, or I can hold on to the handlebars and lift the object vertically, the two actions are exactly equally as difficult. So that's what's meant by a coefficient of friction of 1. So this is quite a high roughness. Most surfaces in contact have a coefficient of friction much less than 1, although it is possible to have surfaces in contact with a coefficient of friction more than 1. Okay, so now returning to my question. Now that I've specified that the coefficient of friction between the disk and the string is equal to 1, what is the largest mass that I can have here on the left while maintaining that the system is in equilibrium? Well, if you like, you can pause the video and try and see if you can work out the answer. Okay, well, I'll tell you the answer. Incidentally, I think it's quite common for people to guess that the answer will be 2 kilograms. But it's not. It's actually e to the pi kilograms. Now, I won't derive this fact in this video. If you want to see a derivation, you can look up the capstan equation. But let me describe basically what this equation says. So, if we pick a point along the contact between the string and the disk, so let's call this point x, then we can ask, what's the tension in the string at that point? So let's call that tension T of x. So this T of x is not a vector, it's just a positive scalar value corresponding to the amount of tension in the string at that point x. And now, if we pick another point, let's call it y, we can ask, what is the factor by which the tension in the string is different at the point y from at the point x? And to be clear, we're asking this specifically for the scenario that the mass on the left is the largest possible while maintaining equilibrium. And the answer is that the factor of increase in tension going from x to y is equal to e to the power of the coefficient of friction, which is just 1, times the angle round the disk that you have to go through to get from x to y. So in other words, what we're saying is, as you go round the disk, the tension in the string increases exponentially with the angle that you make to the center of the disk. And incidentally, we likewise have that the pressure of the string against the disk increases, going round the disk, exponentially with the angle, except that at each of the two endpoints of the contact between the string and the disk, there's an infinitely steep transition between positive pressure and zero pressure. But anyway, this idea of exponential growth with respect to an angle has quite a nice representation in terms of complex numbers, and that's what I want to talk about for the remainder of this video. So let's imagine that the plane that this lies in is the plane of complex numbers. So that's the number plane that I referred to earlier. And let's imagine that the center of the disk is the number 0. And so if we say that the disk has radius r, then we can say that the rightmost point of the disk is the number r, the leftmost point of the disk is the number minus r, and the top point of the disk is I times r. And so in this case, the capstan equation can be expressed by saying that if I take the ratio of the tension at the point y to the tension at the point x, and I raise this to the power I, we get simply the ratio of the actual positions themselves as complex numbers. And incidentally, this equation doesn't just hold in the case that the string performs only one half turn around the disk. If I imagine the case that the string actually gets wrapped round the whole disk some number of times, so then there'll be multiple points along the string that occupy position x, with different tensions at those points, and there'll likewise be multiple points along the string that occupy position y, again with different tensions at those different points. Well, in my equation, I can substitute in for T of x the tension at any of the points occupying position x, and I can substitute in for T of y the tension at any of the points occupying position y, and this equation will still hold true. And now we can actually express this equation slightly more succinctly in terms of a proportionality. So you might be used to the idea of one variable being proportional to the square of another variable, or the reciprocal or squared reciprocal of another variable. But here we have the position, such as x or y, is proportional to the tension to the power I. So not a positive or negative power, but the imaginary power I. So I think this is quite nice. Now let me illustrate our equation with an example. Namely, take x to be the point R, the point where the string first comes into contact with the disk, and take y to be the point minus R, so the last point at which the string is in contact with the disk. So then the tension at the point R is equal to 1 kilograms force, and the tension at the point minus R is equal to e to the pi kilograms force. And so plugging all this into our equation, so for the left-hand side, y over x, we have minus r divided by r, which is just minus 1. And then this is equal to the right-hand side, and in this case, the ratio of the tensions is just e to the pi. And so we end up with the equation that we mentioned earlier, that Gelfond's constant to the power I is equal to minus 1. And so what we have here is quite a nice sort of visualization through mechanics of this equation that Gelfond's constant to the power I is equal to minus 1. Now, to be clear, I haven't in any sense derived this equation because my complex number representation of the capstan equation already presupposes the principles of how raising positive numbers to the power I works. And it's not the topic of this video to derive those principles. But nevertheless, I think that this is quite a nice representation of the equation that Gelfond's constant to the power I is minus 1. Okay, so we've described this interesting proportionality between position and tension. And so if you imagine that we have a device that can measure the tension at any point along the string, then what we've effectively set up is a mechanical calculator for raising positive numbers to the power of I. So I think this is quite nice. Well, that's it for this video. Thank you very much for watching.